Fifth lecture on Bessel function. Today we shall discuss the orthogonality relation of Bessel function. Before going to the orthogonality relation of Bessel function, let me remind what we have done earlier in the case of Legendre, Hermite and Logar polynomial. In the case of Legendre polynomial, we found that dx is delta nm. For Hermite, it is from minus infinity to plus infinity e to the power minus h. This is delta nm, and for Logar we found that so we see that the special function or these three special functions are orthogonal for two different orders of special function n and m. Here for the case of Legendre there is no weight factor, and for the Hermite and Logar there are weight factors. There are another kind of function. This is one kind of function where the special function of two different orders are orthogonal with respect to some weight factor when integrated under suitable limits. There is another type of function which is sine function or cos function 2 pi n x dx mx delta dx integrated from a to b. It is also delta nm, where the capital delta is defined as b minus a, and this integral we have used extensively in the case of Fourier series. And this function may not be sine only, they may be cos as well. Here we see that the same function with two different arguments, one with argument n, other one with argument m, they are becoming orthogonal. The Bessel function that I am going to discuss today belongs to this type of function, where the Bessel function of a particular order but with different argument are orthogonal over an interval. So to say, the orthogonality of Bessel function resembles the orthogonality relation of trigonometric functions rather than the other special functions we have discussed earlier. With this, we come to the orthogonality relation with this introduction, we come to the discussion of orthogonality relation for Bessel function. Bessel function. First kind. The Bessel function of order nu is defined as x square j nu of x d to x This is the Bessel function of order nu. Now we use u is equal to alpha x and replace x by u, so that the equation becomes u square Now we use the value of u, so this is becomes alpha x whole square then alpha x for u this is equal to 0. What we have done in the this expression, we have replaced x by u, and where u is defined by this. So this alpha cancels out. We get x square d2 j nu of alpha x dx2 plus x j nu of alpha x dx, here x alpha cancels out, is equal to alpha square x square minus nu square of j nu of alpha x. The conclusion is that j nu of x, if j nu of x satisfies this equation, j nu of alpha x satisfies this equation, where only in this part alpha is replaced by x is replaced by alpha x, and the argument of the Bessel function changes. So this is one important relation. So we write this equation like this. X square, it will be for future use. This is the relation. Now we consider two constants alpha and beta, so that we define u is equal to alpha x and b is equal to, b may be confused with nu, so we write w. So u is equal to alpha x and w is equal to beta x. And so the corresponding arguments, j nu of alpha x is, for to shorten the notation, is written f, and j nu of beta x is actually j nu of w, is written as g. So here one step, this is j nu of u, which is equal to f. So that if we write the differential equation, that is being satisfied by f and g, they are x squared d2f dx2 plus x df dx plus this is alpha square x square minus nu square of f is equal to 0, and for g we have we multiply the first relation by g and the second relation by f and subtract the second from the first. So the result is x square d2f dx2 g of x. This was multiplied by the minus f times d2g dx2. This is the contribution from x square term, and similarly from this we have x times df dx times g minus f times dg dx. And you see that the nu square term, this when multiplied by g, this is nu square fg, and this is also nu square fg. So this cancels out, and we take alpha square minus x, so minus beta square, alpha square minus beta square x square fg is equal to 0. This can be written as we have done several times in earlier occasions, p of x y is equal to q of x, where the quantity is defined as like this: y of capital Y of x is equal to del f del x times g minus f times del g del x. So when this is differentiated, first term is the double derivative of f times g. So if we this is f double prime g plus f prime g prime, from this f prime g prime minus f g double prime, which is the quantity within the third bracket. So this is indeed this, and p is the function p of x is x by x square, so it is 1 by x, and the quantity q of x is, when this is taken on the other side, this becomes beta square minus alpha square f of f and g fg. This equation has integrating factor if is equal to e to the power p dx. Since p is 1 by x, this is equal to e to the power log x is equal to simply x. So this differential equation has an integrating factor of x, and you see that this is 1 by x. So this differential equation, when multiplied by integrating factor, becomes x dy dx plus y, because x and 1 by x cancels out, and for in this part we write beta square minus alpha square x fg. The left hand side can be written as ddx of x times y is equal to beta square minus alpha square x fg. If we replace the values of f and g, you see that f is defined by this relation and g is defined by this relation. So this equation becomes this equation becomes, we write the right hand side first, x fg is 1 minus beta square minus alpha square ddx of x times y. If we integrate this between limit a to b, or for x, if we integrate it between a to b, we get integration from a to b x g dx is equal to 1 minus beta square minus alpha square. Then we have d of xy integrated from a to b. So this is 1 minus beta square minus alpha square x into y within limits a b. Now we unfold our shorthand notation to write it as A to B x j nu of alpha x, this is x j nu of beta x dx is equal to 1 upon beta square minus alpha square, and this is y x j nu prime of alpha x j nu of beta x minus, sorry, first term is f, this is j nu of alpha x within limits a to b. Now the right hand side can be made to equal to 0 if we say the right hand side is equal to 0 if alternative 1 is the function vanishes at the upper limit. So upper limit, it is, this term is beta b, this is alpha b, and in the lower limit it is beta a and alpha a. So this is j nu of alpha a is equal to 0 is equal to j nu of beta a together with j nu of beta a is equal to j nu of beta b. If this is 0, then the right hand side is 0. Or the second alternative is du at x is equal to a is equal to 0 is equal to dj nu du at x is equal to b together with this is w at x is equal to a is equal to 0 is equal to dj nu dw at x is equal to b, or any other. There is third option, any other combinations. So the right hand side of this equation can be made equal to 0 if this condition is satisfied, or this condition is satisfied, or any other complicated relation. But the popular choice for this is the first one. So one chooses the first one is the popular choice. So we choose A and B such that they are the zeros of Bessel function of order nu with argument alpha x or and beta x. These are called the zeros of Bessel function. When alpha is not equal to beta, with this choice, when alpha not equal to beta, the right hand side is 0. So this is the orthogonality relation of Bessel function of order nu corresponding to different arguments. And what happens to the case when alpha and beta are same. When alpha and beta are same, this is of the form 0 by 0, and L'Hopital rule may be used to determine the quantity at the right hand side. But here we shall adopt a procedure which has been adopted in Lilly-Hobson bench as well as in Matthew Walker for the determination of normality condition. So we have established the orthogonality of Bessel function of a particular order with respect to different arguments, and our task is to find out the normality condition. So what we have then is this relation integration from a to b x j nu of alpha x j nu of beta x dx is equal to 0 if alpha not equal to beta and a and b and x is equal to a and b are the zeros of j nu of alpha x and j nu of beta x. So this condition is that. Now our condition aim is to find out the orthogonality relation, also normality condition. So we need to find out the normality condition. So normality condition is this. We define I alpha beta is equal to, so this is I alpha beta integration. So we define I alpha alpha is equal to x j nu of alpha x square dx from a to b. We switch over from alpha x to u, so that we should multiply this by alpha, this by alpha. So we have 1 upon alpha square u j nu of u du integrated from alpha a to alpha b, because the limits in terms of u is this. We write it as 1 by alpha square some indefinite integral k with limits alpha a to alpha b, where we define the k as indefinite integral u j nu of u du. Recall that the entire calculation will be performed in terms of u variable, and ultimately we will substitute the x. So this, if we integrate by parts, the first term is half u square j nu of u, and if we, the second part is we integrate this. When we integrate this, this is half u square, and when we differentiate this, we get 2 j nu of u and j nu prime of u, where j nu prime is j nu of u du. This differentiation is with respect to u, and these two half factor cancels out. Now recall the differential equation to be which is satisfied by j nu. This is u j nu double prime u square j nu plus u j nu prime u square minus nu square of j nu is equal to 0, or u square j nu, this is the term that appears here, nu square j nu minus u j nu prime minus u square j nu double prime. So this becomes this relation becomes half u square j nu square minus this is not there, so integration u square j nu, this is nu square j nu, this term minus u j nu prime minus u square j nu double prime j nu prime du. So what we have done basically in coming from here to there, we have replaced u square j nu is equal to nu square j nu minus u j nu prime minus u square j nu double prime. This is the substitution. Now see that this can be written as half u square j nu square minus half ddu of if we differentiate first term, this is 2 nu square j nu prime. Here is j nu and j nu prime. If we differentiate this term, the first term is twice u j nu prime square. So u j nu prime square. And if we differentiate this, it is u square j nu prime j nu double prime, and half factor is being adjusted. So this becomes half u square j nu square, and from this term minus half nu square j nu square plus half u square j nu prime square, which can be written as half taken common u square minus nu square j nu square of u plus u square j nu prime square. This is the relation, and so this becomes, this quantity becomes one by 2 alpha square. Alpha square were there and 2 is factor from there. U square minus nu square j nu square of u plus u square j nu prime square of u within limit alpha a to alpha b. As per our choice, the alpha a and alpha b are the zeros of Bessel functions. So this is 0 at the extremities. So we have 1 upon 2 alpha square and here we have u square j nu prime of u, this whole thing square with limits alpha a to alpha b. Whole thing is square. Now we come to the recurrence relation that we have derived in the other class, in the earlier class. In terms of u, the j nu minus 1 of u plus j nu plus 1 of u is equal to twice nu by u j nu of u, and j nu minus 1 of u minus j nu plus 1 of u is equal to twice j nu prime of u. This is basically twice dj nu of u du. Now if we add these two terms, we have j nu minus 1 of u is equal to nu by u j nu of u plus j nu prime of u, or j nu prime of u is equal to minus nu by u j nu of u minus j nu minus 1 of u. This is one relation. Remember that the derivative is with respect to u, and if we subtract this one from this, we get j nu plus 1 of u is equal to nu by u j nu of u minus j nu prime of u, or j nu prime of u is equal to nu by u j nu of u minus let me check the sign. I am subtracting this from this, so this one from this, so this is plus, this minus this, this relation minus this. We are taking it on the other side, so this side must be minus. This is the other relation. Now, as per our choice, the limits at the lower and upper limit j nu is 0. So we don't require to bother these two terms. So this can be written either this one or this one. So there are two more alternatives. One is u, and the minus sign on squaring goes alpha a to alpha b, and second alternative is 1 by 2 alpha square u j nu plus 1 of u, the square is on our entire quantity. This is alpha a to alpha b. These are the three alternative forms for the normality of Bessel function of order nu with arguments alpha. If we write this two relations with respect to x, so we can write I alpha is equal to first relation 1 upon 2 alpha square, and when we write the upper limit, this is alpha square b square, and the lower limit is alpha square a square. So the alpha goes, and we have x j nu minus 1 of alpha x with limits a to b. Similarly, for the other one is twice x j nu plus 1 of alpha x square, this is square, the limit a to b and a to b, and this is square with limits a to b. A popular choice for ab is a is equal to 0. Then it simplifies to, this becomes b square by 2 j nu minus 1 alpha b is equal to b square by 2 j nu plus 1 alpha b with A is equal to 0. These are the orthogonality condition of Bessel function. Here, this relation will be required in connection with the diffraction phenomena from a circular aperture that I will be taking into consideration in the next class. And the last thing is the Fourier Bessel expansion. Any function satisfying Dirichlet's condition in an interval AB can be expanded in terms of Bessel function of a particular order with varying arguments. So the Fourier Bessel series is Bessel series f of x can be expanded in terms of n cn j nu of lambda mu n x. Now, let me specify this. This is the zeros of Bessel functions, which are tabular, which are given in the lecture notes, with the values of alpha, lambda, mu n are given. To be specific, J0, if we take mu is equal to J0, J0 has several zeros. If you know the graph of J0, so this is the first zero of J0, so this is lambda 1, this is lambda 02, lambda 03, etc. If we there should be an x by a, so these are the zeros, and we can use the orthogonality relation of Bessel function, that is, we multiply this by x, j nu of lambda nu m x by a, and integrate it from dx from 0 to a. And on the right hand side we have summation over n x j nu of lambda mu n x by a, lambda mu m x by a dx, integrated from 0 to a. So this satisfies it. This is Cm, and the result is b square, so half times j nu plus minus lambda nu plus minus 1, sorry, j of lambda nu of m. This is the orthogonality relation, so we can find out the expansion coefficient. Here is another thing to remind you that in the case of Hermite, Lagarde and Legendre, we expand the series satisfying Dirichlet condition in terms of special function of different orders, but here the expansion is not with respect to different orders, but a Bessel function of a particular order with different arguments. The arguments are so chosen that it coincides with the zeros of the Bessel functions. We shall apply this relation for the determination of amplitudes and intensity for diffraction, Fraunhofer diffraction through a circular aperture.